In order to prove that the Goodstein sequence can grow faster than all the fast-growing functions, we said there are two claims we need to prove, and before we can prove them, we need to dig into exactly how those gamma sequences from the Goodstein function are defined. We need this complexity measure for ordinals, tau of alpha, which we define as follows. If alpha is 0, then tau of alpha is 0. Otherwise, alpha is a sum of distinct terms with finite coefficients. We can say alpha is omega to the alpha 1 times a natural number c1 plus omega to the alpha 2 times a natural number c2, and so on, down to omega to the alpha k times ck. And here these ordinals should be strictly decreasing. Alpha 1 is greater than alpha 2 is greater than ... alpha k. So this is like the way we normally write ordinals, except that we're gathering up the similar terms and writing them with these natural number coefficients. Then we define tau of alpha to be the maximum of either the coefficient ci or tau of alpha I. For example, tau of omega, which is tau of omega to the omega to the 0, is 1, while tau of omega plus omega is 2, because there are two copies of this term omega. And tau of omega to the omega plus omega is also 2. There's only one copy of the term omega to the omega plus omega, but recursively there are two copies of omega in omega plus omega. So tau is the maximum of the number of times we repeat a single term, and we go recursively into the exponents to see how many times terms are repeated in each of the exponents. In particular, notice that tau of b omega of n is less than b, because when we write a number in hereditary base b notation, we never repeat a term b times. If we were going to repeat a term b times, we would group them up and make a single bigger term. Since gamma I of n is b I plus 1 omega of gi of n, that means tau of gamma I of n is always less than or equal to I. One way to see what tau does, which will be useful for us later, is to think about what happens if we take an ordinal alpha and try to turn it into a number by replacing its omegas with a natural number. We could define b omega b of alpha to be the number we get by replacing each omega in alpha with a b. So b omega 2 of omega is just b omega 2 of omega plus omega is 2 plus 2, which is 4, and b omega 2 of omega to the omega plus omega is 2 to the 2 plus omega, which is 6, and so on. And we notice that in general, b omega b isn't quite the inverse of b omega, because b omega 2 of omega plus omega is 4, but b2 omega 4 is omega to the omega. There is a one-sided inverse. b omega b of b omega of n is going to be n, because there all we're doing is replacing b's with omegas and then replacing these omegas back with b's. But in the other direction, b omega b of alpha might not be in hereditary base b notation. b omega 2 of omega plus omega gives 2 plus 2, which isn't in hereditary base 2, because in hereditary base 2 we would want to combine these two 2's to get a 4. But as long as tau of alpha is less than b, then b omega b of alpha will be in hereditary base b. If tau of alpha is less than b, we never repeat a term b times, so b omega b of alpha is in hereditary base b, and then b omega of b omega b of alpha is equal to alpha. So b omega b and b omega give us bijections between the natural numbers and the ordinals alpha less than epsilon 0 with tau of alpha less than b. And this gives us a good way to describe gamma I plus 1 of n once we've started with gamma I of n. Suppose we know what gamma I of n is, and we write gamma I of n, as we often do, in the form beta plus omega to the alpha, where, as always, omega to the alpha is the last term, the term with the smallest exponent, when we write gamma I of n as a sum of terms. If alpha is 0, then gamma I of n is beta plus 1, and gamma I plus 1 of n is beta. So suppose alpha is greater than 0. Consider the number k, which is equal to b I plus 1 I plus 2 of gi of n. The reason we care about k is that 1 gamma I of n is equal to bi plus 2 omega of k, and 2, k is 1 more than gi plus 1 of n, because the way we find gi plus 1 of n is, by definition, k minus 1. So consider k written in hereditary base I plus 2 notation. It must be b plus I plus 2 to the a, where bi plus 2 omega of b is beta, and bi plus 2 omega of a is alpha, which we said is greater than 0. So when we subtract 1 from k, we keep the b term, and we get I plus 2 to the a minus 1 written in hereditary base I plus 2, and that's equal to the sum over all the a prime less than a of I plus 2 to the a prime times I plus 1. So gi plus 1 of n is b plus the sum over a primes less than a of I plus 2 to the a prime times I plus 1. Now, gamma I plus 1 of n is b I plus 2 omega of gi plus 1 of n. And each of these terms lifts to an ordinal. So that will be beta plus the sum over a prime less than a of omega to the b I plus 2 omega of a prime times I plus 1. Which ordinals are in this sum? What are these ordinals of the form b I plus 2 omega of a prime for a prime less than a? Well, since a prime is less than a, bi plus 2 omega of a prime is less than bi plus 2 omega of a, which is alpha. And tau of bi plus 2 omega of a prime must be at most I plus 1, because a prime was in hereditary base I plus 2. And we're adding up all the numbers less than a, and bi plus 2 omega is the inverse of b omega I plus 2, so we must get every ordinal alpha prime less than alpha with tau of alpha prime less than I plus 1. So gamma I plus 1 of n is beta plus the sum over all alpha prime less than alpha, such that tau of alpha is less than or equal to I plus 1 of omega to the alpha prime times I plus 1. So tau tells us exactly which ordinals appear in gamma I plus 1 of n, and that's going to let us figure out how big gamma I plus 1 of n is. In particular, if delta is less than gamma I of n, and tau of delta is less than or equal to I plus 1, then delta is less than or equal to gamma I plus 1 of n. So gamma I plus 1 of n is smaller than gamma I of n, but as we drop from gamma I of n to gamma I plus 1 of n, we don't skip any ordinals of low complexity. To prove this, take a look at gamma I of n. Again, we write gamma I of n as beta plus omega to the alpha, where omega to the alpha is the smallest term. If delta is less than or equal to beta, then since gamma I plus 1 of n is greater than or equal to beta, also gamma I plus 1 of n is greater than or equal to delta. So assume that delta is greater than or equal to beta. So delta is beta plus delta prime. Delta prime might be 0, but in any case, since tau of delta is less than or equal to I plus 1, tau of delta prime is also less than or equal to I plus 1. So delta must have the form beta plus the sum over finitely many ordinals of omega to the alpha prime times a constant c alpha prime. Since delta is less than beta plus omega to the alpha, each alpha prime in the sum must be less than alpha. Each alpha prime must have tau of alpha prime at most I plus 1, and c alpha prime is at most I plus 1. So the biggest delta can be is the sum over all the ordinals alpha prime less than alpha, with tau of alpha prime less than or equal to I plus 1, of I plus 1 copies of omega to the alpha prime, but that's exactly what gamma I plus 1 of n is. So delta is less than or equal to gamma I plus 1 of n. And this analysis of gamma I plus 1 of n is what will allow us to prove those two claims about the Goodstein sequence that we promised to prove.